So yeah, hi everyone, I'm Jacqueline, and today I'm going to be presenting joint work with Nate, who's over there. And the title of the work is, what is it for a machine learning model to have a capability? And just to give you a sense of the motivation, I've got two documents there. One is produced by the new AI Safety Institute in London, and the other is an executive order from the White House. And you can see that both of them emphasize that capabilities, auditing, and evaluation ought to be a central part of government responses to the proliferation of AI. And that's a theme that has continued across regulatory proposals in the EU, in Singapore, and in China as well. So another sort of motivation, more personal to me, I spend a lot of time with cognitive scientists, and there's this kind of cottage industry that's developing in cognitive science right now, where cognitive scientists take an evaluation that was developed for humans normally in the 80s, and they apply it to LLMs, and then they make cognitive claims about LLM's abilities on the basis of those evaluations. And I think one thing that's really interesting is that people don't always agree about the ability claims made on the basis of the evaluation. So theory of mind is a very good example. If you look, there are like 15 papers where cognitive scientists alternate between saying that LLMs have abilities in theory of mind and don't, and it just goes one after the other. And I think if we're philosophers and we see a situation where scientists agree on what the evidence is, but disagree on how we should interpret the evidence, that's a situation where we think as philosophers we might have something to contribute. So just to really belabor this point, we're told that models have capabilities that are dangerous, emergent, autonomous, surprising, novel, and we're told they have abilities in domains like chemistry, medicine, the law, and programming, just to name a few. But we're never really told what it is for a machine learning model to have a capability in the first place. And it seems like this question is pretty central to what we ought to make of all these regulatory proposals and all these ability claims. So that's what I want to explore in this talk. So the main question is, what is it for a machine learning model to have a capability? And I think it's really important to emphasize that in giving an analysis of model capabilities, we shouldn't silo the kind of philosophical literature and the empirical literature. So in particular, we should aim to be informing empirical model evaluation practice. And we should also take model evaluation into account when analyzing capabilities. So with that in mind, there are kind of two secondary questions which I think are important. So one sort of question is, what kind of evidence bears on whether a machine learning model has a capability? And then another question is, as philosophers, can we say anything systematic about how model works? Can we identify some of its core ingredients? And that's what I'm kind of going to start the talk with. So I claim that the central aim of model evaluation of capabilities is to decide claims like the one on the board. This is an ability claim. M is able to phi, where here M refers to a machine learning model, and phi refers to some capability we're interested in. Two instances of this schema. GPT-4 is able to pass the multi-state bar exam. Claude 2 is able to write effective phishing emails. And you can see how these sorts of claims are the sorts of things that regulators might care about. I want to distinguish this claim from a closely related ability claim, which I won't talk about in this talk. It's this one. It's about users of models, and specifically, it's about what users of models can do with models. So I think this is an important ability claim in its own right, but it's separate from the claim about what models themselves are able to do. Okay, so focusing then on this first claim, M is able to phi, we need to do two things, right, to start off with. We need to say, what do we mean by M? What's the model we're talking about? And we also need to say, what do we mean by phi? Like, what is phi-ing in the situation? So I'm going to start with the second part first. So what do we mean by phi-ing? So I think here it's helpful to look to the social sciences. You face very similar sorts of issues in evaluating people. So generally, what we have here is a latent construct, and we can't observe that directly. What we can do is measure it in certain ways. So for example, happiness is a classic latent construct in psychology that we can't directly observe. What we test for maybe through people's self-reports on happiness surveys. So our proposal is that when we're thinking of what a measure for a capability should look like, we'll call this an operationalization construct, and we'll say it consists of two components. So the first component is a way of generating queries for the capability. And the second component is a success condition. So you can think of these two things together as what it is to phi. The first condition specifies the situation in which we should expect phiing to happen. The second situation defines what it means for successful phiing to have occurred. And you'll notice that that success condition usually applies to model output in evaluations. It's usually a behavioral thing, but it doesn't have to be, right? We could imagine situations where we track properties of models' internal states and use that to inform our success conditions. Just a point on notation, we're always going to choose some particular operationalization constructs. It's unavoidable when evaluating models. So just to make it very explicit which one we've chosen, we'll use this little C subscript to denote the particular operationalization construct we're using. The choice of operationalization constructs is obviously pivotal in determining whether an evaluation successfully motivates an ability claim. I'm not going to talk about what goes into choosing operationalization constructs, often called construct validity in the social sciences right now, but it's something I'm happy to talk about more in the Q&A. So just to give a kind of concrete example of this, suppose we're interested in evaluating whether Kevin can distinguish authentic Ming Dynasty vases from forgeries. Well, what could an operationalization construct look like for this? Well, here's a natural thing we could do. We could find a load of vases, some of them authentic, some forgeries. We could give them to Kevin. And then for each vase, we could ask Kevin to say, is this authentic or is it a forgery? And so in this situation, the queries would just be individual vases. And the success condition would just be whether the prediction Kevin made on that vase matched our label for the vase's authenticity. So just a couple more examples in the domain of machine learning. If I'm imagining evaluating a model's arithmetical abilities, say I'm interested in whether it can add two numbers, integers, then a query would just be a pair of integers. And a success condition might be, does the output the model produces match the sum of the pair of integers? So it's important to note at this point that the query is kind of an abstract thing. It itself is not a model processable input. And that's something I'll come back to in a second. Okay, so I've said mean by phiing. What do we mean by M? This is a question about individuating the subjects of ability claims. I think there are at least two sorts of questions we need to answer in individuating models. So one is about the level of abstraction in which we characterize a model. So it's a question about, do we identify the model with its implementation? Do we identify it with its implementation in some programming language? Or do we identify it with its weights and its architecture? In other words, the mathematical function it computes. In this talk, I'm going to go with the last option. So I'm going to identify models with their kind of more abstract function. The reason I do that is because I think when people attribute abilities to models, they're not really often distinguishing between different instances of the model. So we think that the GPT-2 on my hard drive has the same capabilities as the GPT-2 on your hard drive. But that's obviously something that could be relaxed as an assumption, and we can discuss it in the Q&A as well. The other important aspects of model individuation is distinguishing between the model boundaries and its background conditions. So in the case of evaluating Kevin again, we can imagine we've got these queries, these vases to test Kevin's authenticity detection abilities. But we haven't yet given a full evaluation procedure. In particular, we need to specify various background conditions for the evaluation. We need to specify what the lighting conditions in the room are, whether Kevin is allowed to touch the vases and feel the glaze on them. And these are things that are going to be crucial in assessing Kevin's performance, but they're not parts of Kevin. They're background conditions in our evaluation. So I'm going to use the example of LLMs throughout this talk. I think it's useful to think about what are the sorts of things that could be background conditions in LLM evaluation. And what are the sorts of things that could be potentially parts of the model. So here are some examples of potential background conditions. The first one is a tokenizer. used to thinking of LLMs as things that take in natural language strings and produce natural language strings as outputs. But of course, under the hood, there's a lot of additional scaffolding going on. So first, we need something that converts a natural language string to a list of tokens in the model vocabulary, tokenizer. We also need a method for sampling from the model. So one thing we need to specify is a temperature parameter and a random seed. Like the model gives us a vector of real values over its vocabulary. It doesn't tell us, what output we should take from that. Similarly, we need a sampling procedure. So we need, to pick some particular method of inference. And there's a few there, and there's a few more that we can discuss too. We also need to specify a prompting strategy, and I think I'm going to talk about prompting strategies on the next slide. They're going to be pivotal in how we think about evaluating LLMs. Often when we're engaging with LLMs in practice these days, they're proprietary, and we're engaging with them often, or many users are, for a web application. This adds additional complications in specifying background conditions. So in particular, many contemporary LLMs have content filters on both their inputs and output, where the output content filter will screen out outputs that are deemed undesirable. And the input filter might screen out inputs that it detects as intended to produce outputs that are undesirable. That also seems important to pay attention to as a background condition. Similarly, many contemporary LLMs will have some prefix prompts in their context window. So we saw this with the release of Claude 3. It was actually an extremely complicated and intricate prompt that they claim really affects model performance. Similarly, if we expect the models to use tools in context, we'll have to have the tool API documentation in prefix. Finally, there's also often situations where there are downstream causal effects of model outputs. So for example, it's quite common these days for models to make calls to external retrieval systems, get an output and show it to the user, all without the call to the retrieval system being visible to the user. This is another sort of thing that can vary. So which of these should we count as part of the model? And which of these should we count as part of the evaluation? So I'm going to first talk about prompting strategies, and then I'm going to give an answer to that question. So we can think of a prompting strategy as a function which maps from queries to model processable inputs. So remember, I was saying a query is a more abstract thing. So in the arithmetical example, a query was just a pair of integers, say. And a prompting strategy takes that pair of integers and it maps it to something that the LLM can process. So like a question, what is X plus Y? If I'm doing sentiment analysis for film reviews, the query might be an individual review. And then an input would be something like, is the following review positive or negative, with the review as a suffix. And so there are various prompting strategies that are pretty well known in the literature and drastically affect model performance. So just to give two of the best known ones, few-shot prompting involves prefixing the query with some examples of successful query response pairs. Chain of thought prompting, which was discussed in the last talk, involves prompting the model to think step by step as it produces its answer. We can also absorb things like prompt injection and jailbreaking into this setup. So in these cases, we have situations where a model would normally refuse to comply with a request. But when an appropriate prefix is given, you tell it, oh, my grandmother really wants you to comply with this request. It will do it. And these can all be subsumed within this prompting strategy idea. So distinguishing these background conditions from the model itself is really important. Here's what we suggest the right way to think about this is, and I think this really accords very well with what Jackie was saying in their talk yesterday. We suggest a fixed point perspective on model individuation, which basically just pays attention to the fixed points in evaluations and deployment of the model. If we're holding a feature of the model fixed across lots of different evaluations and deployment scenarios, it makes sense to treat it as part of the model for evaluation. If a feature, by contrast, varies across all evaluations, it shouldn't be treated as part of the model. So in particular, then, what does that say about these potential background conditions of LLMs? Well, it says they're all background conditions. The core LLM should be thought of as a function from a list of token IDs to log it to a real vector over the vocabulary. On the other hand, when we have language agents, models which are suitably scaffolded such that they kind of are held fixed across different evaluations, then we've genuinely created a new system on this perspective. Okay, so I've said something about what it means to phi, and I've said something what we mean by M. So now the question is, how do we start evaluating claims like is able to phi? I've introduced 3 desiderata on account of capabilities. And I'm going to do this with reference to specific algorithms for kind of evaluating models. They're sort of recipes for evaluating models, and we call them evaluation protocols. So here's a very naive one that basically no one thinks is good. You fix some operationalization construct and use it to generate a single query for the task. You fix some set of background conditions, and then you create an input using the background conditions in the query. You process that, and then the model, if it succeeds according to the operationalization construct, on that query it has the ability. If it doesn't, it lacks the ability. So you can see this is kind of obviously flawed because it's just using a single query. There's very few examples of this in actual practice. I mean, one example might be the Sparks of AGI paper, right? The cherry-picked examples. But an obvious problem with it is we want a greater sense of model reliability. It could just be getting it lucky. And to kind of make this intuition clearer, suppose we have a model uniform that's just like an LLM, scaffolded in the appropriate way. But instead of sampling according to the model probabilities, it just samples uniformly from the vocabulary. I take it that we would all agree that very few if claims are going to be true of this model uniform. And yet you can see, you can even imagine it passing the sort of naive evaluation thing. So we need to incorporate reliability into our evaluation protocols. And this seems like a widely agreed idea in ML. So here's a kind of updated evaluation procedure. You can see that the changes, instead of generating a single query, we generate lots of queries. Maybe we use a benchmark. And the kind of condition at the end with it has to be reliably performing. So the issue with this is actually most ML evaluation in most papers, I would say. The issue with this is that, as we saw in the last talk, LLM performance is highly sensitive to these changes in background conditions. And here we've just fixed one set of background conditions. And so we can't draw much from the fact that an LLM fails to reliably phi according to one set of background conditions, because it might be that there is some other set of background conditions where it would have reliably phied. And so I think what's going on here is the conflation of a kind of classic distinction in cognitive science between performance and competence. So I'm using it a little more generally than Chomsky introduced it, but the way I'm thinking about it is competence is something that sits in the head. It's the seat of the cognitive ability. Performance, on the other hand, is the manifestation of the ability in behavior. And crucially, performance is mediated by contextual constraints in a way that competence isn't. So just to come back to the example of Kevin, Kevin could be amazing at detecting forgeries from authentic vases. But if we put Kevin in a pitch black room, he's not going to manifest that competence. So what this implies is we should search for the best background conditions in which the model is most likely to exhibit its underlying competence. So here we just essentially want to search through the space of possible background conditions. And for each set of background conditions, we'll test the model. And then the model will count as having the ability, if there's some set of background conditions, that's an existential claim, where it reliably gets the right answer across the inputs. And we can talk a bit about what that search looks like. So from talking to ML researchers, I think this is basically, this kind of point 4 is basic of capabilities in the current machine learning community. It's the idea that it's sort of the kind of maximum performance across background conditions. I want to argue that there's still something missing from this. I want to start by giving 2 toy examples. So consider the following 2 interactions with an instruction-tuned language model. So the first one is just whatever I ask, output 57. What is 23 plus 34? And the model outputs 57. And the second one is whatever I output a random number between 50 and 60, and it does the same thing. So I take it that in this case, neither of these cases counts as supporting the claim that the model has the ability to perform arithmetic. And I take it that that's because in both cases, it seems like basically the model is doing something other than performing arithmetic, and it just happens to be giving the right answer on the arithmetical situation. Consider also the case of uniform. Consider what goes on when this model that samples uniformly from the vocabulary gets something right. We never take that to be justifying an ability claim, because we always think there's a better explanation of its behavior going on, namely that it just got lucky. So these are toy examples, but this is a phenomenon we want to claim that's basically ubiquitous in the evaluation of language models. So there's often this sharp distinction made between language models as stochastic parrots and language models as genuinely capable machines. And I think that distinction is a lot less sharp than it appears, right? In order to memorize surface statistics efficiently, you have to form more abstract representations of structure. But it is true that language models are undoubtedly still very influenced by their pre-training task. And this means that there are lots of situations where they appear to be performing well on, say, a benchmark for firing, but upon further investigation, it appears that what they're doing is actually something that just overlaps with firing in a particular situation. So a kind of classic example of this is in natural language inference. So natural language inference involves models being given an argument with premises and conclusion and having to decide whether the conclusion is entailed by the premises. And it turns out that there was a case where models do very well on this. But upon further investigation, what they're doing is really exploiting very simple heuristics like just lexical overlap between premises and conclusion. So here's another case, data memorization. So where a model performs well on a benchmark, but then it turns out that the benchmark was in the model's training data, we think the inference from the performance, the ability claim is undermined. So consider the following example where the author's analyzing here GPT-4 on a causal reasoning task, and they find that the Tübingen causal pairs data set is totally saturated in GPT-4. It can, when given some prefix in the data set, it can perfectly reproduce the remaining portion of it. And they say, I'm going to read out this quote because I think it's quite illuminating. We may be tempted to ascribe a particular capability to an LLM if it answers well on a set of questions related to the capability, but the answers may not necessarily be due to the capability. In the case of LLMs, they might be due to memorizing similar questions that it encountered in its web scale training set. So again, you see, we have a situation where we have apparently successful performance, but we want to block the inference from successful performance to the ability claim. And our thought is maybe we can in some way build this into our analysis of what it is for a machine learning model to have a capability in the first place. And our proposal is pretty simple. It takes this very venerable tradition in philosophical analysis of abilities, namely to add in a conditional element to our analysis of abilities. So in the kind of classic conditional analysis of abilities, someone has an ability to X if they would do X if they try to do X. So it adds in this conditional if they try to. So on our picture, which we call the conditional analysis of model abilities, or CAMA for short, M is able to phi under an operationalization construct C, if and only if there's some set of background conditions B in which the following conditional reliably holds across queries. If the output M produces is best explained by its being directed at phi seeing, then M successfully phi sees. So we call this best explained condition trying. It's kind of nod towards a sort of instrumentalism about trying, but nothing we're saying at all hinges on it actually counting as trying. You can think of it as trying star if that would be helpful, but I'm going to refer to it as trying just as a shorthand. So obviously, to evaluate this proposal, we need to say something about what we mean by best explained by being directed at, right? That's the crucial part of this. So there's a kind of question in philosophy of action when you have a sort of teleological explanation like this, does it ultimately bottom out in a or explanation involving an internal cognitive state of the actor. And I'm happy to talk more about how we should think about that question in this context. But now I just want to give a kind of proof of concept that this is a thing that can play a useful role in model evaluation. So specifically, I want to look at the kind of signature of explanation, which is that explanation enables counterfactual prediction. And every theory of explanation agrees on this. So the thought is that if we can find some appropriate set of counterfactuals to look at, where we can disambiguate between things the model is actually kind of trying to do and things it's unintentionally doing, then maybe we can actually test meaningfully for whether this conditional is satisfied. And so the obvious starting point with this is just a behavioral test for trying. With this behavioral test, we just consider perturbations on inputs. So we say that an output Y is best explained by being directed at, or just well explained by being directed at phying if the following two conditions hold. So it should be sensitive to perturbations to the input which are relevant to phying. That is, its output should change when we do those sorts of perturbations on the input. But it should be insensitive to perturbations to the input which are irrelevant to phying. So its output shouldn't change in those situations. Just to illustrate how this could work, consider again these two toy examples. So in both these cases, we thought that what was going on was that the model was doing something other than doing arithmetic. And what it was doing just happened to match up with what it would be doing if it was successfully doing arithmetic. Well, now we can just test that using a perturbation, right? So in the first case, intervene on that 57 in the user's prompt. If I make it a 56, we would expect, and indeed if you try this, it will happen, the model's behavior will change. It will be 56. And that's a perturbation that's irrelevant to the query that we're interested in, right? The query is 23 plus 34. So it implies it fails the behavioral test. It's not actually trying to do arithmetic. And similarly, in the second case, if I say change the plus sign in the query to just the word plus, the model's behavior will also change. And yet, again, it seems like what was going on there is not that I've made a meaningful change to the actual thing I'm testing the model on. And so just to make clear, this isn't just an application to two toy examples. This is exactly the sort of thing that machine learning people do if they want to test for the kinds of issues we identified before. So in order to diagnose those kind of shallow syntactic heuristics, the authors had to find a data set where the kind of heuristic exploitation came apart in its predictions from the actual natural language inference task. So they had to essentially perturb the inputs in a way that it responded in this way. And similarly with memorization, what we do to test memorization, right, is to replace something we think has been memorized with a query we don't think has been memorized, but otherwise bears exactly the same structural features. Maybe we just vary the lexical content. So, I mean, this is a behavioral test, right? This is just a very early, obvious implementation of this conditional idea. And it has obvious limitations. So we talked at length yesterday about the need to go beyond behavioral testing, because obviously this sort of perturbation of inputs can't distinguish between capabilities which have the same extension. It's there's no intentionality here. It's all extensional. And another limitation, of course, is that sometimes it's very unclear what we should count as a phi relevant or a phi irrelevant perturbation. So in particular, if I'm testing a capability that involves a lot of sensitivity to the precise content of the utterance, say I'm testing a capability of the model to translate some particular author's work or something like that, then any perturbation I make to the input is sort of, by definition, relevant to the capability. So I think what these considerations suggest essentially is there'll be situations where in order to test this trying condition, we'll have to look for non-behavioral means. So we'll have to look for counterfactuals that involve interventions on the model's internal representations. And I think there's plenty of kind of empirical work that could be applied to this, and happy to talk more about how that would work. So I just want to give two general kind of applications of the proposal I've suggested. So the first is just, what if we put this in some way? What if we embedded it in a more general evaluation protocol? Well, in that case, we would just have kind of a very similar evaluation protocol to before, but we would basically throw out queries on which the model didn't actually count as trying to do the capability, because essentially those queries would be counted as irrelevant to our assessment of whether the model actually has the capability. It's trying to do something else, so we can't judge it actually has an ability to phi. We call this kind of just rejection sampling. Yeah, so this is, and I just want to emphasize that step 4, we could test for trying using that behavioral test, but we could also use a non-behavioral test there. It just seems like a generally best practice. And I guess one thing I want to say is, as I said, I think there are cases, and we saw in some of the work I discussed earlier, there are cases where ML practitioners are doing this. I think what's going on in those cases is they don't take themselves to be doing the same thing. And so I think what is nice about this proposal is it kind of unifies that body of work and sort of explains and motivates it across different things like testing for memorization, testing for heuristics, and this sort of thing. So I don't take this to be like an especially revisionary proposal with respect to ML evaluation practice. I more just take it to be a kind of concretization of what I already think is kind of floating in the air as best practice. So there are a few more applications that I think are a bit more conceptual. So I spoke earlier about content filters on model outputs in particular. So say we have a situation where a model has a content filter on its output such that there is no situation in which it ever produces an undesirable output. In this situation, do we want to say that the model has lost its capability to produce undesirable outputs? I mean, it's kind of a classic issue that occurs in like the philosophy of abilities. I think, so our kind of way of thinking about this is the model still retains its more general capability, but it loses a deployment-specific capability. When you fix some feature of its deployment environment, say you fix a content filter, it no longer has that ability in that deployment environment. And so in the language of kind of the new disposition lists about ability, we would say that it's been masked, its ability in this environment. So one distinction our account makes is between two different things that can affect behavior. So one thing that can affect behavior is in case the model is trying to do something, its likelihood of succeeding at it. But another thing that can affect behavior is just whether the model tries at all, right? This is now a distinction we have, and the degree to which it tries. So I think this distinction can be used to analyze differences amongst different prompting strategies and also differences amongst different tuning techniques effect on models. So just to contrast again, few-shot prompting versus chain of thought prompting, I think what's going on in few-shot prompting often is that we're using the prefix to kind of pin down what we want the model to do. So in this situation, we're using the prompts in the prefix to get the model to try to do phi rather than to try to do psi. And we think that if we encourage the model without this, it might end up doing something psi that's not what we want it to do. By contrast, with chain of thought prompting, when we encourage the model to think step by step, it's already trying to phi, but what we're affecting is the kind of conditional. When it tries to phi, how likely is it to succeed at phiing? And we're influencing that because we know that producing these extra steps in processing generally across lots of different capabilities will help it phi. So there's kind of distinction there, I think, between affecting the propensity to try and affecting the conditional. When you're trying, do you succeed? And I think that distinction again applies to tuning techniques like RLHF. So I think there are a few different reasons to think that RLHF doesn't really affect a model's underlying capabilities that much. So Firstly, it involves relatively few parameter updates compared to other training steps. Secondly, it's easily undone by fine-tuning. Thirdly, as we've seen, things like prompt inject attacks can kind of bypass it, implying that the capability is still there somewhere. And finally, if you look at the effect of RLHF on the model's actual output distribution, often what's happening is you don't really see a change in the ordinal ranking of different tokens. What you do see a change in the cardinality of different token probabilities. So in particular, you generally see a higher concentration of probability mass, like the entropy of the output distribution decreases generally with RLHF. Well, so then I think what we can say about RLHF is it clearly has a very large effect on behavior, but it doesn't have a large effect on the model's capabilities. And kind of now we have a way of explaining that. What it's affecting is the model's propensity to try to exhibit the capability of some of these harmful capabilities. And then lastly, I just want to finish by noting that maybe this provides a kind of way of some steps towards thinking about fair intermodal comparison. So I think one of the reasons we're interested in comparing models to one another is because we think that in their training will lead to meaningful differences in their performance, right? They've been trained on different data, often using slightly different techniques, slightly different architectures. And we think there is something meaningful about those differences such that it's worth evaluating them and comparing them. But if we think that, it would be surprising if we didn't also think there would be differences in the performance constraints that models face. And actually, that was alluded to in the last talk, right? Some of these open source models in particular are very sensitive to small changes in prompts in a way that more of the kind of frontier proprietary models aren't. And so often what happens, what we'd like to do, right, is standardize our evaluation across models. And what that really means is standardizing performance constraints that models face. But I think the issue is, in practice, the way that is implemented is we standardize the background conditions. We fix some set of background conditions and evaluate all models across the same set of background conditions. But as I've said, I think there are large reasons to think that that is actually giving different performance constraints to different models. And I think we should expect that trend to continue, especially as more and more data is proprietary, there are more and more architectural developments, and so on. And so what we'd like to do is, for each model, find the set of background conditions on which it performs best, right? That would be the really, truly fair test of model comparison abilities against one another. I think the problem and the reason people don't do that is because it just feels too gerrymandered and arbitrary. It feels that you could just find some set of conditions where the model succeeds, where it doesn't, but maybe you don't find them for another model. And I don't have a general solution to that, but I think one thing that this distinction draws out is that you can rule out a large class of those gerrymandered prompting conditions, because you only can rule out any prompting strategy on which the model isn't trying to do the thing you're interested in. So it gives you kind of a starting point for fair model comparison. You look for the prompts on which the prompting strategies, the background conditions in general, on which the models are actually trying to fire, and then you compare models in that way. Okay, so that's been quite a lot of content. I would really love to hear all of your thoughts. Thank you so much.